Today's goal is to define rigid transformations and then also be able to identify rigid transformations. So let's start with some vocabulary. A rigid transformation is any method that moves an object so that the result has the exact same shape and exact same size. If we break this vocabulary term down into its two parts, rigid, that word means firm, and then transform means to change. And so what we're saying is that we are changing where the location is of the shape, okay? Transforming means we're changing the position, while at the same time we're keeping the shape firm. We're keeping it rigid, meaning that it stays the same shape and same size. So if it was a triangle to start off with, it's still going to be a triangle when we're done moving it. Now, there's only 3 rigid transformations. You may have heard of some of these before. One of them is called a reflection, one of them is called a translation, and the last one is called a rotation. We're going to go through each of these with examples. But before we do, we need to know some vocabulary words. One of the vocabulary words is the word pre-image. Pre-image means the original shape. Okay, pre-image is the original. Now, in contrast, the shape where we've moved it to, okay, so like the second shape or the copy, some people like thinking of it as the copy, we call that one the image. All right, so the image, we're going to call that's the new shape after we're done moving it. Now, sometimes when we have the two shapes, whether it's on our paper, graph paper, sometimes it's hard to tell which shape was the original and which one's the new one, especially if we have both. And so mathematicians have a symbol that we use so that way we can tell them apart. And you may have already noticed what that symbol is. We call it the prime symbol. And when we use that prime symbol, it's called using prime notation. Right? The symbol that I'm referencing here is that little tick mark symbol on the letters. So that little symbol, it's kind of like an apostrophe. Okay, I know it might look like the number 1. It's not a number 1 though, it's just a tick mark. And that symbol tells you that that shape is a copy of the original shape. Okay, so A prime is the copy of point A, B prime is the copy of point B, and then C prime is the copy of point C. All right. So let's take a look at each of these 3 rigid transformations just so that way we can tell them apart. All right, the first one we're going to talk about is called a reflection. A reflection is probably one that you run into in your daily lives because a mirror creates a reflection of yourself, right? And so you can look at yourself in the mirror and you can see how yourself is flipped. These 2 examples in the diagrams here, these are both examples of reflections, and you may notice really quickly that it's just like a mirror. On one side is the original, and on the other side of the mirror is the flipped version. To be able to do a reflection or to be able to recognize a reflection, you're going to be looking for one component. Okay, so this is for reflections. The one thing that you need to look for is you need to look for a line of reflection. Essentially, that's like the mirror. And in both diagrams, you can see a dotted line. That is the line of reflection. Okay, that's the mirror that's doing the copying. And that line of reflection will always be exactly halfway between the 2 shapes. In fact, that's part of how we can define a reflection. It turns out that the original shape is going to be a specific distance, okay? So if we want to know where the copy is going to end up, we can measure, how far is the original from that line of reflection. Let's say that it's, I don't know, let's make something up here. Let's say that it's 3 inches away. And if that's the case, it turns out that the new image is going to also be 3 inches away, just on the other side of that line of reflection, or in other words, on the other side of the mirror. And that's exactly what happens no matter what part you measure of the shape. It's always going to be the same distance away. So if we measured like this point to the line of reflection, that's going to be the same distance on the other side as well. All right, so it's literally we're copying the distances from one side of the line of reflection to the other side. Same thing happens on graph paper, so we can measure those distances off graph paper or on graph paper. So for example, the original one here is point Q, so the black shape is the original, and we can count on the grid that it is 4 units away from the line of reflection, and so that's why on the other side, the left side, it's still 4 units away. If you were asked to identify where the line of reflection is, like that pink line, if it wasn't there, but we did have the two shapes, we could figure out the distance by counting, like from point Q to point Q prime, and then just wherever halfway is, that's where the line of reflection is going to be. Let's take a look at the second rigid transformation. The next rigid transformation we're going to look at is translations. Now the word translation sounds a lot like transformation. Look how similar these two words are. Transformation is a broad category. Okay, a transformation is all three of the types of movement, whereas the translation is just one of those types. All right, so a translation is a slide. This is a very common type of movement in real life as well. You can remember that translation means a slide because the first two letters of slide show up in the word translation. And what it means is it's when you shift a shape or an object up, down, left, right, or a combination of those. And to be able to do a translation, there are two things you need to know. Okay, there are two components to be able to do a translation. One of them is you need to know a direction to move the shape. All right, so that would be like the up, down, left, or right. And then once you know the direction, you need a distance. So in other words, how far are you going in that direction? And so this example here with the ice cream cones again is a translation. And oftentimes in real life, we will describe translations like this with two translations. A lot of times we will split this into like an up-down translation and then a left-right translation. So instead of going on a slant, right, we'll say, oh, this shape was moved, maybe it was moved 2 units up and then, 5 units to the right. And so it's convenient to be able to break it down into the two components like this just because it's easier to understand and it's easier to communicate. There are ways to do it all in one single translation. So it is possible to do it in one slanted movement. In the picture with the triangles, notice how we can also count it as like an up, down, and a left, right by using the grid. So for example, focus on just point G and point G prime. We can move point G 3 units to the left, and then we can move it down. Oh, that was a poor color choice. Let me choose blue here. We can move down a single unit. And it turns out that the same pattern happens for all 3 points, which makes sense. We're moving all of them 3 to the left, and we're moving all of them down 1, and that's how the the whole shape gets moved. Notice how just like in the reflections, all of the shapes, it's the same shape, same size, you just moved to a different position. And same with the reflections. I don't think I specified that, but notice how the ice cream cones and the triangles are the same triangle, same shape, just different place. Now the third type of movement is called a rotation, and a rotation is like a turn. We encounter this in our daily lives as well. Mostly, like the wheels of a car is a great example of something that rotates. And to describe a rotation, it requires 3 components. All right, so the 3 pieces of information that you have to have in order to do a rotation or identify one is, first, you need to know where the point of rotation is. The point of rotation, here's an example of one, that is like the center of the wheel. Okay, that's where everything is spinning around. And I'll draw the rest of the wheel. Imagine, the wheel is around that center point. Okay, so I'm drawing this pink circle. I know I didn't draw a very good circle, but imagine that dot, that green dot, is in the center of the wheel. And that way you know where everything is spinning around. The second thing you need to know is you need to know the direction of the wheel. Which way is it spinning? And just like the wheel on a car, it can spin, make the car go forwards, or it can go reverse. Most of the time we will describe the direction with 2 words. One word is clockwise, and clockwise means it's going the same direction as a clock. So clockwise means, going this way, just like the hands on a clock. And then the opposite of clockwise, the word we use is the word counterclockwise. Let me just try this real quick here. All right, so we can say counterclockwise, or occasionally you might see it called anti-clockwise. And those both mean the opposite of a clock. Let me also change the picture here. So instead of going the same direction as a clock, it goes the other way. Right? The third thing that we need to know to be able to do a rotation is we need to know an angle measurement. And that angle measurement tells us how far we're spinning before we stop spinning. So a small angle would mean we turn the wheel a small amount, and then a big number for the angle would mean we're turning the wheel further. That angle measure is actually measured right here. You can see those two dotted lines pointing to the two ice cream cones. That angle right there is the angle measurement that needs to be specified. So when we put all three of those together, we can figure out where the wheel is, we know which way the wheel is spinning, and we know how far to turn that wheel before it stops. We can also do it on graph paper, and it works the same way with those same three components. Let's identify them real quick again. We've got the point in the center of the wheel, okay, and so that means we need to draw a circle around that point of rotation. We're drawing a wheel here around the center point, and so let's just pick point L to start with. So let's say we're moving point L to L prime, and we know that there's going to be a circle that it's spinning around our center point. And if you look closely enough, you might see that point L does in fact move around that particular circle. And we could say that it's moving in a counterclockwise direction because it's going opposite direction of a clock. And then we would be able to also say how far it's spinning. So if we connected point L and point L prime to the center, we could measure this angle, and that would be how far it's spinning. In this case, it's spinning by 90 degrees. You can see that right angle there in the middle. And then we would do the exact same steps for all the other points. They're all spinning as well. They're all spinning 90 degrees. They're all spinning on a circle around point P. So that is the rotation. That is all for today. Like and subscribe.